All right, good evening. Let's finish up our lecture from today, lecture 15, and then lecture 16 will be online. We set up a lot of concepts today, and we talked about Km and Vmax. We said what they were, we defined them, we even said how to get them from the data. So if you review all that and if you get that firmly in your head, then you can talk about what can we do to compare different enzymes. We can measure this for any enzyme we can measure product for. So now we can say what's our Km or Vmax and how do we compare different enzymes that have different ones. The first thing I want to mention is I want to say that there is actually one of the issues with hyperbolas is that they bend, right? And it's hard on like graph paper. You can sketch a line, but it's hard to sketch a curve. It's hard to know how your data fit to a curve. So it's much more easy in lab, especially for those who are starting out like us, if we have a straight line version of the hyperbola that we can actually use in lab. And this is actually important on your worksheet. It's important in literature. It's even in your reading. You have a straight line version of the hyperbola that you do by just doing, it's not fancy math. All you do is you take the reciprocal of both sides. Because notice that this is a y equals x over x plus constant graph. That makes a hyperbola. The whole problem is that the bottom of the fraction on the right side is our x value plus a constant. That makes it curved. So to uncurve it, you know what you have to do? Flip it over. So you put the plus sign, instead of on the bottom, on the top of the fraction. You take the reciprocal of both sides. So all you do is you take your Michaelis-Menten and you do this. You do it as 1 over VO equals S plus Km over V max S. All of a sudden you look at that, that's not a curved line anymore. You separate that out, you end up having S over S on the right, and that ends up being a constant, 1 over V max, and you have 1 over Y equals slope 1 over X plus 1 over intercept. And this is called the Lineweaver-Burke equation. And this is actually much easier for us humans to look at. It's hard to tell if a hyperbola fits the data right. It's easy to tell if a straight line fits the data right. And so this, again, this is one of those things, this derivation is actually pretty simple. It's probably my third example of a simple derivation. If you go back in time, you can name this after yourself. Who knows, maybe Lineweaver is a time traveler. But so the Lineweaver-Burke equation is exactly this. This is exactly the same equation. But if you draw this, it's a straight line. And the cool thing is if you look at it, it's y equals mx plus b. There's our y, 1 over v. And you see you have that on the y-axis. 1 over s, you have that on the x-axis. And so then you have a slope that is equal to your Km over Vmax. And then your intercept is right here. It's 1 over Vmax. In fact, the fact of the matter is your x-intercept is also meaningful. Your x-intercept is negative 1 over Km. Although honestly, x-intercepts are a little bit weird, so most people prefer just to use the y-intercept and the slope. Either way, you can get a lot of information, and you can fit it with just a ruler and graph paper. You don't need a fancy computer to fit a straight line. So you're going to see some examples of that, and actually we're going to talk about what it means when you change things, when you do something to the experiment and then measure that line again. Okay, so what do they all mean and what are the normal ranges for each? First off, let's talk about Km, the Michaelis constant. Remember that has a definition. It's 3 little k's put together. It's the 2 k's that go out of ES over the k that goes into ES. In other words, it's the rates that are taking away from ES over the rate that is adding to ES. Notice how that actually looks like a dissociation constant. If you have the dissociation rate, K off over K on, you get the same thing for KD. So all that is to say, you can actually look at this and we can ask questions about, like we said, the prominent situation was where K2 is rate limiting and slow. So it's very small relative to K minus 1. If that is true, then if K2 is much less than K minus 1, K2 plus K minus 1 is approximately equal to K minus 1. The K2 is so small, it disappears. And so we can say that Km is equal to the dissociation of ES over the association of ES, which is almost exactly like the definition of the KD of ES. So if our assumptions are correct, then we can look at it and we can say The Km looks like a dissociation rate for E plus S. We just have to neglect what K2 is, and as long as it's a small number, that's an okay approximation to make. Now you have to worry about this, like if K2 is not so small. If there are multiple steps after K2, we have a lot of assumptions here that we've done to make our math simple. Then Km is a mixture of values, so you can only say it is approximately, squiggly line, Kd of Es. It is not equal to the Kd of Es. With that in mind, though, we can sort of look at it and we can sort of say most of Km is going to be like a binding constant, a dissociation constant, for enzyme and substrate. And if we look at it that way, we can line up a bunch of different enzymes. Here's a bunch of different ones with a bunch of different substrates. We can say what their Km is. And remember, these are actually, if you remember the KDs that we talked about maybe micromolar, nanomolar, even picomolar KDs. Those were tight binding. These are not tight binding. These are millimolar or micromolar over here, like right here. This glucose is 50 micromolar. So it's weak in terms of if we looked at like antibody binding. But it's enough for the enzyme to do the job. And remember, enzymes are not supposed to be that great at binding substrate. They're supposed to be good enough. So actually it makes perfect sense that we would have a Km that is in the millimolar to high micromolar range, which is what we see here. And you can even compare different substrates. Hexokinase in the brain binds ATP with 400 micromolar. It binds D-glucose with 50 micromolar, but D-fructose with 1500 micromolar, which is 1.5 millimolar. I'm saying it this way so that you get used to these different prefixes, because it's the way biochemists talk. Now notice that the one that stands out, what's the worst binding enzyme here? It's the one with the biggest Km. And that's catalase at the top. So that's kind of weird. You know, why do we even call catalase an enzyme? It looks like it has a 1.1 molar binding constant, if that's all that's going on. So I just want you to say, oh, that's weird. We can compare these. We can say the other ones look normal. This one looks weird. Here's some Km values of other enzymes, including chymotrypsin with a particular substrate. We have a bunch of other things. There's pyruvate carboxylase down here. A lot of these are going to be discussed in Biochem 2, so you will see them again. For example, pyruvate carboxylase, if you look down here, it binds pyruvate sort of medium tight with 400 micromolar affinity. It binds bicarbonate more weakly with 1000 micromolar, and it binds ATP more tightly with a 60 micromolar. And again, we're approximating because we're just using this like a dissociation constant. But for these kind of comparisons, it's valid. It works. So this fits in with the paper because the paper is reporting a big K that is like a binding constant. So you want to be thinking this way when you look at it. So when you're reading the paper, you want to focus on two things. There are drugs with good Ki values, which is like Km. Good will be smaller in this case. How could they fit in the site? The ones with the lower Ki values are going to fit in the site better. And so you're going to say, okay, is this real? Are there probably good specific interactions? Or maybe is it a weird non-specific interaction where it's not really fitting in the site very well. It just has like some kind of major overriding interaction for which there could be a mistake. You want to see if it makes sense. A lot of specific interactions make sense for binding. Only one or two non-specific interactions, you're not sure about the conclusions. So you want to look at that. And you also want to look at the strength of the evidence for chloroquine and hydroxychloroquine. We actually will talk about that more. Those are inhibitors, and we're going to talk about that more in the inhibitor lecture, which is the one coming up, lecture 16. But these are the focuses for your reading. So I want to tell you right now, this is what you should really be looking at. And understanding this, you look at the rest of the paper to understand the context. So for example, the paper has this. It shows these four structures, and each of these has a different Ki associated with it. Now these are computer predicted Ki, so you want to look at them and you want to think about, where's this Ki coming from? Why is the computer saying that this hydroxychloroquine and chloroquine, the computer is saying that they have good interactions? Okay, Is all its eggs in one basket, in which case we don't trust it? Or are these distributed specific interactions, in which case we trust it more? Well, lo and behold, they have this table right here, where they take each of those compounds, and again, this is not the best communicated paper, but you have to deal with what the scientific literature gives you. So this is something that tells you what the computer found as the amino acids that interacted with each of the different compounds. And so what you have to do is you have to use your organic chemistry brain, and you have to look at this. For example, this right here is the binding mode of the protease with dipyrimidal after the MD simulations. That means the computer said that it bound this way. Dipyrimidal has a 0.04 micromolar affinity. That looks pretty good. What does the computer say? Where does the computer say this affinity is coming from? So we look at compound 1, and we look over at this row. It says that it has an interaction with phenylalanine 140, with serine 144, with glutamate 166. I put little colored arrows with each of these for where each of them are. And so it says that it actually has a phenylalanine 140, and it doesn't even actually show that on this figure. So you have to think a little. You have to put your, you have to look for, where is phenylalanine 140? Well, it is right next to asparagine 142. In fact, it's 2 away because that's the pattern for beta sheets. Beta sheets point up and down every other residue. And so that means F140 has got to be right here where the green arrow is. If it's making a good interaction, what kind of interaction is it? It looks like it's some kind of ring stacking interaction. It's like a hydrophobic interaction where the rings stack up on each other. Oh, that's decent. The blue arrow, serine 144, it's around here. It's on the other side of asparagine 142. And maybe that serine could be making a hydrogen bond to this nitrogen. That also looks like a good specific interaction. And then finally, glutamate 166, that is a negative charge, also can hydrogen bond, and they're actually showing that one right here. They're showing it hydrogen bonding specifically to this little OH in the dipyrimidal. That is how you look at this, and I want you to, they show you how to do it for this one. They show you the structure right here. You look at the interactions, and you come up with an idea. This looks like 3 good, strong, specific interactions. I believe this, at least as much as anything else. This is what you want to do for compounds 1 through 16. For all of those, you can say to yourself, do these make sense, or is there just like one interaction that it doesn't really make sense to me because it looks like the computer could be wrong? The computer can be wrong on one thing very easily. It's a little bit harder more convincing for the computer to be to tell you 3 specific things that make sense, because even if one of those is wrong, the other 2 are right. And so that's how you look at this. So I've just told you exactly how we want to review this, and we're going to do that on the test review day on a week from Friday. Okay, so for example, here's the dipyrimidal. Here's the number 2, which is the candesartan solexitel. You see right here, number 2 appears to have histidine 163, serine 144, and asparagine 142. Well, our serine 144, it bound here for the dipyrimidal, is what we're thinking. And so we're going to be looking for something like that with the candesartan solexitel. We're going to be looking for something like this nitrogen, a nitrogen on a ring in the middle of the molecule. Well, maybe that is this right here. We're not sure because they're not telling us all the information. But that's part of the point of this paper. It's what do you do when they're not telling you all the information? So let's finally move down to compound 4. Compound 4 is the 4th one in the row here. It's chloroquine. Compound 4 has one interaction to glutamate 166, and we know that glutamate 166 is off to the side of the pocket. The question is, what's that doing? Oh, well, glutamate 166 has a negative charge, chloroquine has a positive charge. Probably what we have is the computer is saying, I see a good interaction between glutamate 166 negative and this positive charge. Great. But that's all it sees. That seems non-specific. A charge-charge interaction doesn't need to be specifically oriented, and it's possible that the computer can be fooled once. It's not giving you 3 ideas, it's giving you one big idea. So it could be wrong, it seems non-specific, and I don't trust this as much as I trust the dipyrimidal. You've got that information for all 16, so you can look at them and say, do you trust it or not? And when you're doing that, you're essentially looking at KIs, which is a version of KD, which is like KM. It's all binding constants, so we want to learn how to look at those. All right, so that's all about the Km. What about Vmax? And remember, Vmax is defined as K2 times E total when K2 is rate limiting, the normal situation. What about when something else is rate limiting, even if you don't know what it is? So we want to have a more general definition than saying K2. It sounds like we're too certain that it's the second step. So what they do is they call it Kcat. We don't know anything about it except that it is the rate limiting step of catalysis. So that's why we call it Kcat instead of K2. For our purposes at this level, they're pretty much the same thing. And so Kcat is the most general form of Michaelis-Menten equation. And the beauty of Kcat, and by the way, I just want to check something right here. Okay, good. I think we are good. The beauty of Kcat is it's just a first order rate constant. It's a simple exponential decay. It's the kind we talk about in physical chemistry all the time. So it's just a simple number that you can say to say how fast does my enzyme go. And so look at these. Usually you get Kcats in about the 100,000 to 1,000 range. Okay, this one at the bottom, the Rec A protein, is really slow. 0.4 is a small number, therefore it's a slow enzyme. What about catalase? Remember that we were kind of wondering how it could be an enzyme if it has such bad binding? Well, now we see. It is bad binding, but it's super fast. It's 40 million Kcat compared to 100 times carbonic anhydrase, which is itself on the fast end of the scale. So that thing that tells us that catalase is sort of an asymmetric enzyme. It doesn't bind to substrate super well, but once it does, it converts it right away. So it's super fast once it gets a hold of the substrate. So is catalase a good enzyme or not? You can't just say it is a good enzyme or not, but maybe if we have this number for Kcat and a number for Km, maybe we combine the two numbers that tell us something into one other number that maybe combines their insights of each. Just some other examples of Kcat numbers, turnover numbers, same thing. You see that they tend to be about 100,000. You can get some pretty slow enzymes at the bottom, but we're talking about in the 1,000 range as sort of average for enzyme speed. So when in doubt, use both. Low Km is better and high Kcat is better. So if we put them together, and if we put Kcat on the top of a fraction, Km on the bottom, we get a single number that if it is bigger, it's better, called the specificity constant. That's pretty simple, and so biochemists like to use that to talk about things. So for good enzymes, we're going to have a large Kcat Km. And if you look at these enzymes, you can have Kcats that are ranging in the thousands, Kms that are ranging in the micromolar to low millimolar, and those come out to be Kcat Kms that are all similar. They're in the 10 to the 8th, 10 to the 7th range. So that's cool. And look at catalase right there. So catalase has a bad Km, but a super good Kcat, and on average it comes out to be a perfectly good average enzyme, a Kcat Km of 4 times 10 to the 7th. So we have numbers, and we can ask you homework problems about those numbers. Here's another table of more enzymes just to give you more examples. Once again, we have 10 to the 8th to 10 to the 7th, and superoxide dismutase wins the prize for best enzyme by this measure because it can get all the way up to 7 times 10 to the 9th. This is unusual. It's got an unusual combination of fast Kcat and strong binding Km. So I want you to look at these enzymes in the table before. I wanted to put this on a worksheet, but we already had enough worksheets. So instead, I'm just going to show it to you right now. Look at the tables, and we have table enzyme A, B, and C. And if you say which enzyme has the highest affinity of substrate, assuming everything's normal, just look at Km. How do you know? Because Km is approximately equal to a Kd constant. So highest affinity for substrate will be the smallest Km. And that's going to be, take a look at it and see your answer. That's going to be enzyme C. Okay, so which enzyme can convert the most substrate to product in a given period of time? Well, this would be Kcat, right? And instead of looking for the smallest Km, we're looking for the biggest Kcat. So I want you to look at that one and try to decide which one has the fastest enzyme. Okay. Looking at that, it's enzyme B. Enzyme C has the highest affinity, enzyme B is the fastest. Which enzyme has the highest catalytic efficiency? Now you have to pull out your calculator and you have to divide your Kcat by your Km. And I'm looking at this, it's a little bit close, so you can't be sure without calculating. But I will leave that to you to calculate and see which one it is. It's actually a pretty simple calculation. You just do a fraction and then you compare the numbers. Bigger is better for this particular measure. And here are some more Km values of enzymes. We can talk about things like, you can look at the different substrates. Sometimes you'll have different substrates that bind the same binding site, and then you can compare the binding of the binding site and maybe even come up with a hypothesis. This one with the better affinity, lower Km, fits into the substrate better. It will interact with more amino acids, things like that. So the final thing to say about this, the other thing you can measure in the lab is you can change the pH. And there's something interesting here, because most enzymes do have an optimal pH. Most enzymes have evolved to work at pH 7.4. And lo and behold, if you measure enzyme activity versus pH, glucose 6-phosphatase has its middle at around pH 7. So we can say, okay, that's cool. We can actually go into more detail and we can talk about which titratable group has a pKa that would explain both sides of this. The other kind of enzyme we can look at is pepsin. And if we were in class, I would ask you, where do you think pepsin comes from? It comes from where it sounds like. Peptic, it means stomach related. And so pepsin is going to be a stomach acid. And that is confirmed if you look at the pH. The pepsin is very unusual. It only works at pH of 2 or below. It works best. So you can draw a nice little bell curve like this, but you can also get information out of it. For example, for chymotrypsin, you have a typical looking enzyme activity where you have the overall rate is maximal around pH 8. Okay, great. It works fine at pH 7. Everything's good. What you can do is you can actually mutate. You can actually mutate residues, and or you can break it down, because we can not just measure rate, we can measure Kcat and Km. And if we do a graph of Kcat versus pH, look at this. Kcat drops off when you gain protons. So we know that this Kcat is associated with His 57, like this goes away if you mutate His 57. So even more than that, His 57 is important, because the Kcat drops off when you add protons. That means that the His 57 must be unprotonated, deprotonated, in order to work. If you push a proton onto it by increasing the pH too much, the His 57 will be protonated and the Kcat won't work anymore. The other thing that you can look at is you can look at this same graph. This is chymotrypsin, but you're just looking at 1 over Km versus the V. You're doing 1 over Km because, again, smaller is better, so you're making the smaller number higher on the graph. So right here we have the same pH maximum around 8, but the 1 over Km is not affected by making it more acidic. If you make it more basic, then you get the behavior that you see in the total graph. You see the activity fall off. And so we actually trace this to the isoleucine 16 backbone amino group, and it means that if you take the protons away, it stops working. It stops binding to the substrate. So therefore, the IL-16 backbone amino group must be protonated, and that explains graph C. This is kind of a cool way, and this is the way that they got the information. When we talk about enzyme mechanisms and we say this proton has to be here, it's this kind of experiment that actually told us, in combination with other experiments, what had to go on. Just remember, the enzyme is at or near its pH optimum. Two things have to be true. It has to have tertiary structure stable, and it has to have all catalytically active residues in the proper protonation state. So if you change the pH, you could be changing one of those residues like we showed on the last slide. But you could also be just unfolding the enzyme. It could be stopping to work because you've just unfolded the enzyme rather than doing something specific to the mechanism. The way to really prove that is to do to break it down into kcat or km, and to see something where it stays flat in one case, where it drops off when you look at the full rate. All right. So this is the end of lecture 15. We're going to move on to lecture 16, and those are going to be posted by Friday. Now you can complete most of the 6A and also the first 6 problems of 6B. Lecture 16 will take up the second half of 6B. So why not get started on it now? You'll have lots of homework, and the next test is coming up pretty fast. The other thing is, before lecture 16, I would like you to look over section 11.3. It's posted on Canvas under Friday's module. There's no reading quiz because I can't figure out how to do it, but and it's okay because it's a relatively short thing, and I'm going to talk about most of it anyways. But it would really help for you to do some reading of it before you log into those videos on Friday. All right, so I will see you virtually on Friday then.